I do historically underestimate the love of nerds to do weird things. It's true.
You're listening to Marianne Writes a Programming Language. And I'm Marianne. When I first started releasing episodes of this series, a few people asked me to put them up on YouTube as well as the traditional podcasting channels. This is going to be the episode where that comes in handy. Today, I'm going to talk you through how to take the output of a parser generator and build an evaluator loop on top of it that can run programs. If you find yourself thinking, I can't really visualize what she's talking about, I encourage you to look this episode up on YouTube because the YouTube version includes screen caps of code that might make it easier to understand. Funny enough, my first draft of this series didn't include this episode. That's the challenge of learning things. Once you understand them, they begin to feel obvious and trivial, and you forget that they have to be explained to other people. Right. So, if you decided to write your own parser, then the question of how you connect the parser output to an evaluator loop is simple. But if you're like me and you wanted to leverage the mature tools that exist to do some of this stuff for you, it is not immediately obvious what you should do after you fine-tuned your grammar and generated your parser. A parser is not a programming language. I've been using ANTLR to generate my parser and lexer, so some comments will be specific to that, but the general concepts will be applicable to other tools, so you should be able to follow along if you've chosen something else. In the language I'm building, I don't want global functions. Therefore, when we think of a grammar as breaking a file into smaller and smaller chunks of valid code, there are only three types of code that can be in the program: declarations, assertions, and for statements. The for statements I'm referring to in this programming language are a bit different than you're expecting, because stock flow models are themselves designed to run in a bounded loop. The for statements in my language are not for loops. They're basically configuration settings for the model's internal loop. But I digress. Insertions aren't really that important at this stage of the language development, so that leaves just declarations. The first level of our grammar is the spec file. The second level is a set of declarations. The third level are all the possible declarations: constants, stocks, and flows. Stocks and flows have properties and methods, some of which are required by default. By this point, you should begin to see how this forms a tree. At the root, we have a spec node. Under that, a declaration node. Under that, the specific type of variable that we're declaring, maybe a stock node. Within that node, we have a series of property nodes. Under the property node, maybe a function definition. Under that, this is what the parser will create. It will use the grammar to define how to break source code up into a set of nodes arranged into a tree. Then it will walk that tree for you. But walking the tree isn't executing the program. That's the gap we need to write code in order to fill in. In ANTLR, part of our generated code will include something to walk the parse tree, either a listener or a visitor, depending on how you configure ANTLR. A listener will walk the entire tree from the top to the bottom and then back up, executing your custom instructions as it goes. A visitor will only move forward if you tell it to advance to the next node, which can be useful if you don't need to consider the full program. For example, part of the REPL I built to do user testing outputs a visualization of the model, but that visualization only cares about what flows are connected to which stocks and how. The rest of the code isn't relevant. So that's a situation where I used a visitor instead of a listener. Both visitors and listeners will generate a set of hooks for each node. So what you do is extend the default class that ANTLR has generated, be it a visitor class or a listener class, and overwrite those hooks with custom code that extracts data from the node and assembles something executable out of it. In a prototype language, what this means is that I have a hash map where I store defined variables. When we walk the parse tree and encounter a declaration node, we pull out the identifier from that node, often a child node of the declaration, and turn it into a key in our hash map. Then we pull the assigned value in the declaration node, again, often a child node of the declaration node, and store it as the corresponding value. This is super easy when the values are static, strings, numbers, etc. But what do we do when we store a function? Well, we store it as a tree. I suppose you could store a copy of all the relevant child nodes from the parse tree, but I actually found it easier to create a simple AST. That's abstract syntax tree, if you're unfamiliar. ANTLR's parse tree has a lot of information in it, after all. And parse trees tend to contain nodes that accurately represent the syntax of the grammar, but are not important to the execution of the code. Building your own AST is not super difficult. Essentially, every node needs to store some information about its type and then a value. The node value will either be a child node, a set of child nodes, or a static value like a string or a number. Since I wrote the prototype in JavaScript, I can get by with having one node class, the type being stored as a string in a property. When I start building the real language in Go, each type of node is going to need to be defined as its own type in Go, because Go will enforce strict assignment of the node value property, which means it can't be a single child node or a slice of nodes or an int or a string. We have to define exactly what it's going to be up front. So we have to define a different node type for each node we want to use. I mentioned before that when we extend ANTLR's generated visitor or listener class, we get hooks for each node of the parse tree. We will have code that triggers when we enter a node. The name of it is enter, followed by the node name as it is defined in the grammar, and depending on what language ANTLR is compiling it to, it may be enter plus node name plus the word context, or enter plus node name. The best way to know for sure is to open up the auto-generated visitor or listener file and check. And then there's code that triggers when we're exiting the node, as the walk is moving back up the tree. That has the same naming convention as the enter hooks, just with the word exit instead. Most of the time, you'll want to use the exit hooks. We'll talk about why in a second. We build the AST by wrapping data from the parse tree node at the very end of the branch in the right AST node type and pushing it onto a stack, which in most languages will either be a list or an array. That's why the exit hooks are so important, because we want to start from the bottom where the data is and pass the AST nodes up. That way, when we want to get to the part of the parse tree where we define our function and assign it a name, the AST that we want to represent our function is sitting on top of the stack, fully formed, waiting for us. As we move up from the bottom node, whenever a higher node has valuable information that we need to sort of add to our tree, we pop off the top of the stack, wrap that value in another node capturing this new information, and push the larger tree back onto the stack. So for example, let's say I have the expression x plus y. We have a node representing x, a node representing y, and we want to wrap them in a parent node called addition. Using this structure allows us to create complex algorithms with the same code we do for simple ones. A plus B plus C is just an addition node where one child node is C, and one child node is another addition node with the child nodes of A and B. Building ASTs is useful because most functions will make use of values passed to them at runtime, so you can't execute them while walking the parse tree because they may not have been defined yet. When we finish walking the parse tree, what we have is a hash map populated by all the named variables and the values assigned to them, and all the named functions, and the trees that represent the steps they execute. Since stock flow models operate in loops, walking the tree gets everything defined and assembled, and then the process of executing the model loop pushes the new trees into an eval loop. The eval loop is a function wrapping a giant switch statement. The value being tested in the switch statement is the type of the node being passed to the eval loop. And each case typically calls the eval function recursively and passes the node's child. If the node has multiple children, the case block will call eval on all of them one by one, sometimes in a for loop or sometimes in a different construct depending on what the node actually does. So our x plus y example from before would operate like this. The switch statement would evaluate to a node type addition. And the code in that case block would probably be something like return eval parentheses left node close parentheses plus eval parentheses right node close parentheses. When the eval loop executes on the left node type is a variable, and the code in the case block would probably say something like look for a variable by that name in the hash map and return that value. In this way, we work down the tree until the eval loop encounters a value it can actually return, and then the recursion completes by passing those values back up. The best way to understand how this works is just by doing it a bunch of times. Every time I work on an implementation, I get a little bit better at it. But if you're thinking to yourself that building an interpreter or a compiler over and over again sounds like a lot of work, you're right, and I have a suggestion. To help with my suggestion this week, I asked my friend Sarah to come on the show. Sarah is another strange looper who I also know through Pittsburgh-based hackerspace and community group Code and Supply. Hey Sarah, what are you working on now?
Currently working on a side project called Codethesaurus, which is a polyglot developer reference tool. So the idea is if you know something in one language and you're wanting to know how to do the same thing in a different language, you can look it up in the tool and kind of compare them side by side without having to read entire sets of documentation. You can just kind of see a quick glance at a chart and kind of know the difference between the two.
So if you hear a little background noise, that's because Sarah's completely adorable cat, Theodosius, keeps swatting at her microphone. Anyway, back to my suggestion. Esolangs. If you want practice tying everything together, work on a few esolangs first. Sarah, do you know what esolangs are?
I believe they're esoteric languages.
Yes, they are. They're this fabulous world of really weird, strange, completely compilable, valid programming languages, right? But
languages that are basically hey, I don't think we should ever do this, but let's do it anyway.
Yeah, wouldn't it be great if we lived in a world where we programmed only in white space?
Something you would never really want to do, or only in symbols, or only in colors.
Yes, actually the only in colors ones are the ones that I like the best. So is it Piet or Piet? I'm never quite clear how it's supposed to be.
Call it Piet, but yeah, I don't know if I know the exact pronunciation of it either. Piet.
Because it's someone's actual name, and so there should be I should have done the research.
I think it's an artist name.
Yeah, it is. But I'm looking at some of the programs that people write with this programming language, which is essentially just about interpreting colors and pixels. They're gorgeous. People have done almost meme style portraits in this language, and they've done a beautiful rainbow mosaics in this programming language. And I wouldn't say that any of those programs are useful, right? Mostly I think what gets written in esoteric languages are hello worlds of various types that either print hello world or print the name of the language is super popular.
Yeah.
Or they do calculator. This is how you program a calculator in this particular language. What's not clear to me is where the line between an esoteric language and a domain specific language is. How useful do you have to be before you're a domain specific language?
I don't know if I know where that solid boundary is either, but I would say, typically you want a programming language to be readable and writable and easy to convey your thoughts in the form of code. And esoteric languages are almost never any of that.
That's true. Well, I think like we do, like as programmers, care about the look of our code, right? But esoteric languages are almost inevitably like this bizarro world where the actual look of the source code is more important than what the source code does or how efficient it is at doing it, right?
Yeah.
So
And they're usually proof of concepts. Like, can we actually use lolcat as a way to write a programming language? Well, it turns out you can.
Oh, I love lolcat so much. Can we talk a little bit about what is lolcat?
Yeah, so lolcat is like the memes of the cats that like, oh, I can't have cheeseburger kind of nonsense. And like the embodiment of what if your cat were to actually talk to you and has bad spelling and bad grammar. But it's like, what if you implemented that as a programming language? Like, oh, hi, oh, space HAI would be like the introduction to your program. And, like I can has variable name would be like to set up a new variable. And I don't even remember too much past that, but it's like you can have these things and they're typical statements and they're not super easy to parse, kind of like if you took Shakespeare and decided to write it in lolcat, like it's doable. It's not readable and you may have to sit there scratching your head for a little bit, but you can convey the same thoughts. And so like lolcat is one of those, it's more just silly.
I gotta say,
like out of like completely out of the box, like Piet or white space or some of the other ones.
I really love how they'll call ends blocks in kfxby, right? I want to do that in normal programming languages. Like it's just way more satisfying to write kfxby instead of like end, right?
Yeah, sure. Well, Python has some of that really readable text in some ways, and COBOL even kind of has some of that.
Yeah. But interesting that you bring up Shakespeare, because did you know that there's also an esoteric language called Shakespeare?
I believe I've heard of it. I don't know that I've really looked into it that much. But
so this is what I find really interesting about esoteric languages is like kind of a weird, like bizarro world form of like prioritization in code is that Shakespeare, the programming language, is a programming language where your commands are meant to sound like lines from a Shakespeare play. And your like entire source code, it has to be architected in a way that mirrors like stage directions. But in order to accomplish this, they do a couple of weird things. So they essentially sort, it's like a very keyword heavy language, and they sort nouns and adjectives into categories of like positive numbers and negative numbers. And so every noun is like a positive number of 1 or a negative number of 1. And then you use the adjectives to sort of build upon them. So like say like I will add an adjective to a 1 value and that gives me a 2 value. And if I add 3 adjectives to 1 value, I now have 4, and so on and so forth. And so it's like ridiculously complicated. But one of the critiques I read about Shakespeare, which I thought was interesting, is that it's actually that kind of control flow is actually very similar to assembly. But Shakespeare itself, like all the implementations of it, are essentially kind of more transpiler than they are interpreter and compiler. So like the main implementation of Shakespeare will like parse your Shakespeare and then write C program based on like what it's found in your program. And there's one I think that does it in Python. And then what you're running is really a C or a Python program. And since Python ultimately compiles to C, I guess ultimately it just ends up being a C program. But what's interesting to me about that is that if like your actual structure of your esoteric language is kind of mirroring the pattern of assembly, like why are you translating it to a high level language that ultimately gets compiled down to assembly, right? Like we're just kind of going around in a circle in order to like get this joke of like, hey, we got a programming language that looks like Shakespeare.
Yeah, but I think you also underestimate not only the love of nerds to do weird things, but the love of nerds to go, I bet we can't do this. Watch me.
I do historically underestimate the love of nerds to do weird things. It's true.
Because I I believe also you're writing a programming language, which is also kind of this like, hey, nerd, can I actually do this?
Yeah,
sort
no,
of a thing.
that's totally fair. It is 80%, hey, can I do this thing nerdness, and like 20% this thing might actually have a useful function in problems that I face and other problems that other people face. It's true.
And you've heard of like ook, the language ook, right? Which is
No, I
supposed to
haven't.
be based on the sounds of monkeys. So like ook would be, oh, okay. So it's either ook period would be like maybe the start of a program, and like ook period ook question mark would be
Wow.
like create a variable, and ook question mark ook period would be something like, add together. And there's a whole list of the different ooks and the combinations of them that perform different actions.
Oh my
and
God.
how you
I've
do this,
pulled-
but it's supposedly Turing complete, if I remember correctly. So
I've pulled this up on esolangs.org, which like literally is the ultimate guide for every bizarre programming language that exists. And it's just like looking at the Hello World program. It's just like it's ook ook. Ook, 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 ook. Like it just goes on like that forever and ever and ever and ever. Ook is a David Morgan Marr, so Danger Mouse creation. And like this seems to be like, it seems that David Morgan Marr really does very little except like draw cartoons and then write esoteric programming languages. He is the creator of Payet that we talked about before. He's the creator of Chef, which is similar to Shakespeare in the sense that you're trying to get it to look like something else, but you're trying to get it to look like recipes instead of Shakespeare. And like there are at least 8 different esoteric languages attributed to him. One of them I'm pulling up now is called Zombie. It's a zombie-oriented machine being interface engine designed for neuromancers, pure and pure evil ones. Programs run in a multi-threaded environment where there are every kind of entity, zombie, vampire, ghost, demon, daijin, and they all act in a slightly different way. A program is a list of entity declarations stating the action that each entity must perform. Oh, it's like a declarative language. It's sort of like the trolley version of Prolog.
I like that description.
I now kind of want to write like a model validator in Zombie and like see how that would work.
Oh dear. And you've heard of like the emoji language, right? Where every commands are just emoji symbols.
Yeah, that's true. Emoji language. Like some of the ones I was looking at today is there's a language called Don't, which is described as it only has 3 commands. Command H prints hello world. So the hard part is done for you, basically. The question mark teleports the user's device to a landfill in Dubai, which seems useful, like, depending on what computer you use. And then
I can dig that.
Is G open bracket, close bracket, which deletes don't from existence. And then the explanation of don't is, unfortunately, someone ran the G command in one of their programs while testing an interpreter, causing the language to be removed from everyone except the creator's memory. It was rendered impossible to implement. So there you go.
This language doesn't sound Turing complete.
No, I don't think so. I don't think so. There's also Retina, which is based entirely on regex. So like no syntactic sugar, just pure regex in case you wanted to put all of the bad parts of programming into its own language. There you go.
I'm constantly amazed at, I feel like every time I look at this site, they've added like a whole ton more languages to it. Like I'm always just baffled at the absurd lengths people go to. I mean, like some of them are kind of fun and interesting, like some of them are made as jokes. Some of them are made to be funny, but some are made to like absolutely just screw with people's heads.
But I think in general, like esolangs end up being really useful learning tools because their very design usually relies on an extremely limited grammar and extremely limited like vocabulary set. So you don't have to think about like, how do I implement like all sorts of complex data structures in order to like design a parser, a lexer, and the ultimate evaluation loop. You can kind of just start off with a really simple scope.
and kind of like work those muscles over and over and over and over again as you need. You've been listening to Marianne Writes a Programming Language. A transcript of this in every episode is available on the dev community. Just go to dev.to/Bellmar. That's dev.to/BELLMAR. This week, we're also kicking off a book club. We're going to be reading Thinking in Systems, a primer by Donella Meadows. So if you've had this book on your reading list for a while, this is a really great opportunity. Information on how to sign up is in the transcript of this episode.